Hello students, I am going to briefly introduce you to iterative methods for solving a system of linear algebraic equations. As you know, in many computational fluid dynamics problems, we have to deal with a set of linear algebraic equations which are basically obtained after discretizing the governing equations at each and every discrete node. Now, for an example, we consider as shown in figure 1 a two-dimensional plate that is subjected to different temperatures on the bottom wall, right side wall, top wall, and left side wall. This entire computational domain is divided into, as you can see, 5 number of nodes along the x direction and 5 number of nodes along the y direction. So while doing so, we can see that the nodes 1, 2, 3 lie on the bottom boundary. Nodes 8, 13 and 18 lie on the right boundary. Nodes 19, 20, 21 lie on the top boundary, and nodes 4, 9 and 14 lie on the left boundary. And we have only the nodes 5, 6, 7, 10, 11, 12 and 15, 16, 17 as the interior nodes where we have to find out the numerical solution. We are interested in this case to find out the steady state temperature distribution inside the plate. So for this, the governing equation is given by equation 1, where del square t del x square plus del square t del y square is equal to 0. So as we can see here, there are two second order partial derivatives, which when we convert into discrete form at any arbitrary node ij takes the form of equation 2. And as you can see, this equation 2 is basically a linear algebraic equation. But if you see any arbitrary node ij, it has 4 surrounding nodes, I plus 1j, I minus 1j, I, j plus 1 and ij minus 1, whose temperatures are also appearing in the discrete equation. So if we consider as shown in figure 2 node ij as point P, then node I plus 1j will be the point towards the east of point P. We mark this as capital E. The node ij plus 1 will be towards the north of point P. We mark it as point N. Node ij minus 1 will be towards the south of point P. We mark this point as point S. And node I minus 1j will lie towards the west of point P, and we mark this as point W as shown in figure 2. Accordingly, equation 2 can also be recast as shown in equation 3, where AS, AW, AP, AE and AN are the coefficients attached with the points south, west, point P, east and north respectively. And these values are given in equation 4. We can see that these coefficients depend on the mesh, that is the size of the steps along the x and y directions, and that is what we are showing in equation 4. When we apply equation 2 or equation 3 to the discrete interior nodes, we find 9 discrete algebraic equations. These are shown from equation number 5 to equation 13 in this slide. Now in equation 5, if we observe, it is related to node P. So for node P, its south point is node 1 and west point is node 4. Both of these lie on two different boundaries. So these are not basically parts of our solution because they lie in the boundary, and the boundary conditions are supposed to be known before solving for the solutions at the interior nodes. Hence, though they appear in the discrete equation 5, we can carry over the terms associated with these nodes to the right hand side of equation 5. Similar treatment can be done with the other equations as well, and then we can combine equations 5 to 13 in matrix form as shown in equation 14. Now here we can see that A is a square matrix whose size is 9 by 9, where 9 is the number of unknown variables or the number of interior nodes where we want to find the solution. So in this case, you see vector phi is the vector of unknowns containing 9 elements. Likewise, vector B is also a vector containing 9 elements. And then this equation 4 can be actually viewed as a system of linear algebraic equations of the form matrix A into vector B is equal to matrix A into vector phi is equal to vector B. We can see that when we are using 5 number of nodes each along the x and y directions, then we have 5 minus 2 into 5 minus 2, that is equal to 9 interior nodes and that many number of linear algebraic equations. However, in real practice, we are going to deal with much many number of nodes. Say if nx and ny are the nodes along the x and y directions, then we shall have nx minus 2 into ny minus 2 number of nodes in the interior domain and as many number of algebraic equations to deal with. So all these equations, that is equation 14 as we have already mentioned, can be written in the form of matrix A into vector phi is equal to matrix B. We all know for if the number of equations is less, for example, say 3, then we can use the exact methods like Gauss elimination or substitution methods. But when we have more number of nodes or more number of discrete equations, this exact methods becomes cumbersome and mostly impractical. So what is the way out to find out the solution for this kind of problems? The solution lies in the iterative methods. Now any iterative method to solve a system of linear algebraic equations given by equation 15 can be written as shown in equation 16, where m and n are also coefficient matrices whose sizes are the same as that of matrix A. Vector B is the vector of known terms and it is also having the same size as the solution vector A, and K is an iteration level because we have to keep on iterating from one level to the next. Now again, while doing so, by definition, when convergence is attained, the solution in the k plus iteration is going to be the same as the solution in the kth iteration, and that has to be the actual solution phi. So theoretically saying equation 17 is valid at convergence, and hence equation 17, when we substitute back into equation 16, we find equation 18 that gives m minus n into vector phi is equal to vector b, and when we compare equation 18 with equation 15, we basically find that the difference of the matrices m and n is equal to basically the coefficient matrix A, and then we can write matrix n is the difference between matrix m and matrix A, and the vector capital B is equal to the vector small b. Small b is already known, and matrix A is already known because we know our system of linear algebraic equations, but we don't know its solution at this moment. Now, depending on how we choose matrix M or matrix N, we get different iterative methods. The question comes, how should we choose our matrices M and N? Basically, if we observe equations 16 and 19, we see that the number of iterations will be less for convergence if we can easily compute the term that is product of matrix A and vector phi from the kth iteration. So this is basically easy by default because matrix N is already known provided we know matrix M from equation 19, and vector phi from the kth iteration is also known. That is why we are proceeding to iteration level k plus 1. So the right hand side of equation 16 is basically known, and for faster convergence matrix M should be easily inverted. The third requirement is that matrix M should be as close to A as possible, or in other words, M should be a good approximation of matrix A, then we can attain a faster convergence. So just like we have just mentioned that we get different iterative methods depending on our choice of matrix M. Now we are going to discuss two very basic iterative methods. The first one is the point Jacobi method. In the point Jacobi method, matrix M is chosen as the diagonal matrix of matrix A, and if it is so, then matrix N, how will it look like? All the diagonal elements of matrix N will be 0, and the rest of the elements will be the negative of the corresponding elements of matrix A, because from equation 19 we see that matrix N is equal to matrix M minus matrix A. Now if you put this into a matrix form, we can visualize the point Jacobi method as shown in equation 21. So we'll start from the unknown at the first node. We call this as say phi 1. Once we obtain phi 1 in the k plus 1 iteration, we shall move to phi 2 in the k plus 1 iteration, likewise phi 3 in the k plus 1 iteration, likewise at the end it will be phi n in the k plus 1 iteration. And if we see any ith row, that means the iterative equation to find out the ith unknown phi, we can visualize this equation as, you see, for the ith row the coefficient is aii, because you see for the first row the coefficient in matrix M is a11, rest all the elements of that row are 0. So we'll get, if we get the first equation, will be a11 into phi 1 at k plus 1 iteration is equal to the right hand side. The second equation will be a22 into phi 2 in the k plus 1 iteration is equal to the right hand side, and likewise and so on. But what will be the right hand side for the ith row? We shall see in the right hand side, it will be actually summation of the product of, say, mth column of the ith row and the mth row of the 5 vector. But it will not include the diagonal elements, because the diagonal elements of matrix N are all 0. So for any arbitrary row, ith row, equation 21 becomes aii phi I in the k plus 1 iteration is equal to summation from j equal to I to j equal to n, but it does not include actually j equal to I, because j equal to I corresponds to the diagonal elements of matrix N, which are already 0. So what we do, we add the diagonal elements and we subtract the diagonal elements, and when we subtract, this get added up with this summation convention. So that's why we get j equal to 1 to j equal to n minus aij phi j from the kth iteration. And when we simplify these terms and divide by the coefficient of phi I, that is aii, we get that phi for the ith row in the k plus 1 iteration is equal to the right hand side. In the right hand side, all the terms are known. And this is the point Jacobi iterative method. Now the Gauss-Seidel method. In the Gauss-Seidel method, matrix M is chosen as the lower triangular matrix of matrix A. Therefore, matrix N will have 0 as its elements of the lower triangular matrix, and the rest of the elements will be the negative of the corresponding elements of matrix A. Accordingly, when we apply the approximations of matrices M and N to equation 19, we get the matrix form of equation 23. Now let us see any row in the left hand side of equation 23. So say let us see the third row. It will be A31 into phi 1 in the k plus 1 iteration plus A32 into phi 2 from the k plus 1 iteration plus A33 into phi 3 from the k plus 1 iteration is equal to the right hand side. Now in the right hand side, basically for the third row, you see first 3 columns have coefficients of 0. So it will be basically from 4th column onwards. So product of 0 into phi 1 from the kth iteration is 0, plus 0 into phi 2 from the kth iteration is again 0, plus 0 into phi 3 from the kth iteration is again 0. Basically it will be from the 4th column of the third row, that is minus of A34 into phi 4 from the kth iteration plus B4 will be the right hand side of the 4th row in equation 23. Likewise, for the ith row, we can express this in this form, that is j equal to 1 to j equal to I, aij phi jk plus 1 is equal to j equal to I plus 1 to j equal to n minus aij phi jk plus bi. Now, when we are in the ith row, by the time the solutions from I equal to 1 to the value of I equal to I minus 1 are already obtained. That means when we are in, say, third row, by the time the solutions from the first and second row are already obtained in the k plus 1 iteration. So up to the I minus 1 row, the solutions in the k plus 1 iteration are already known by the time we are in the ith row. So that's why the solutions from j equal to 1 to j equal to I minus 1 from the k plus 1 iteration are taken to the right hand side, and then you can see this equation. Now here you see the summation convention is from j equal to I j equal to 1 to j equal to I minus 1, and the second summation is from j equal to I plus 1 to j equal to n. That means it does not include the column corresponding to j equal to I. So we add and subtract the column corresponding to j equal to I, and that is what we get this equation. And when we subtract this equation by the coefficient of phi I, we get equation 24, which is the Gauss-Seidel iteration method. Now here in equation 24 and the equation before that, the superscript latest actually refers to values from the k plus iteration for j equal to I minus 1, j less than or equal to I minus 1, and for I less than or equal to j is less than or equal to 1, latest means the kth iteration. So what we are doing basically in this Jacobi method, we are using the latest values of all the solutions which are already computed by the time we arrive at the equation for obtaining the solution at a particular node. Now here there is a further augmentation of the Gauss-Seidel method, that is called the point successive over relaxation method. So here, in order to obtain faster convergence, the second term in the right hand side of equation 24 is multiplied with an over relaxation factor omega, whose value is greater than or equal to 1. It is found that normally for omega between 1.1 to 2, we obtain faster convergence with the same accuracy or similar accuracy as that of Gauss-Seidel or point Jacobi method. So that is given by equation 24. So